Welcome to On the Metal, Tales from the Hardware Software Interface. I'm Bryan Cantrill. With me, as always, Jess Frazelle. Hey, Jess.
Hey, Bryan.
Joining us as well is our boss, Steve Tuck. Hey, Steve.
Present.
All right. Keep us in line. And Jess, you want to introduce who we have in the garage with us today?
Yeah. So today we have Amir Michael. And yeah, we're hanging out in the garage like usual, talking about hardware and going to production with hardware. So we're really excited to hear all the stories that he has to tell because he has a lot of experience in this area.
And Amir, welcome to the garage.
Thank you. It's great to be here.
You are a true child of Silicon Valley. You grew up here. You're a local.
I am born and raised in Foster City, California.
There you go. So your parents must have been in tech?
My dad was in tech. My mom was a teacher. My dad came here in the early 70s and studied at Berkeley and joined Fairchild Semiconductor. He had a couple internships, and once he finished, he joined one of the pioneers of Silicon Valley when they were actually making silicon in the valley.
That is
That's
amazing. Cool. So, and do you remember him working at Fairchild? I mean, did you?
Not at Fairchild. By the time I was born and have memories, he was already at AMD.
Wow. And so you must have had stuff lying around the house. Was he bringing home interesting things?
Oh yeah. They had wafers that they went through the fab process and which got rejected. And he would bring them back home in carriers, and I'd take the wafers and hang them up on the wall with some tape. And that's how I decorated my room with wafers.
Whoa, that is so dope. Instead of like those glow in the dark stars, it's so much better.
Okay, so how old are you at this point putting wafers up on the wall?
I was in elementary school, I think. Yeah.
That is, when you be child of Silicon Valley, this is a true child of Silicon Valley. This
is
dope.
dope.
A bedroom adorned with wafers.
Versus posters.
Yep, exactly. And he'd also bring back these small plastic boxes that they would put finished chips in them. And I would take the chips and store them somewhere else and use the boxes to keep my Legos in them. Yeah.
That is awesome. And so were you messing around with electronics then at that age, or how are you getting into it?
Oh yeah. I think by the time I was in 5th grade, I'd already learned how to solder. My dad taught me how to connect some batteries to motors and lights, and the wires would keep popping off. So eventually he trusted me with a soldering iron, and I learned how to solder wires and devices together. And I'd try and fix toys sometimes with solder. Didn't always stick, but I've been doing electronics since a really young age. Yeah.
But this is like post PC revolution, right? Because we're in the late 80s at this point. I mean, I don't mean to date you too much here, but late 80s, early 90s even? Or,
yep.
Okay.
Yep.
So, I mean, a lot of kids are playing with software at this point, but you're in the hardware.
Yeah. Not that I didn't play computer games, right? We had XT was my first computer. I think it ran at 2 megahertz and maybe a little faster when you hit the turbo button. But yeah, I was into electronics. I loved building circuits. I loved attaching motors to different devices, making them spin. If it was Lego, I'd put a fan on it and it would blow the car around the living room or whatever it was. I just always liked the physical nature of it, but being able to put something together and actually feeling and touching it. I would buy kits and go to Radio Shack and buy parts and put together different types of kits and sensors. I remember once I put a motion sensor onto a buzzer and hid it under my bed. But anytime anyone walked by it, it would start to beep and startle them. My mom was not happy, especially when she came in to clean my room or vacuum or whatever. But it would annoy her. But those are the types of things I love doing.
That is great.
That's cool.
Jess, do you know what the turbo button is? He mentioned the turbo button.
I of course know what the turbo button is.
You don't have to be so indignant. There's a generational divide. You don't always know what.
But I have a computer inside with a turbo button.
Okay, well, I have found there's an entire generation that does not know what the turbo button is. So just wanted to.
I'm not a part of that generation.
All right, that's fine. There's going to be a future generations that are not going to know what Radio Shack is. Sadly, that's another one that's a little more recent. So I grew up messing around with hardware, scaring your mom.
Yep.
And then when you went to school, you knew this is what you were interested in, or?
Oh yeah, even before that, I would. We had our own computer. It took a while until my dad agreed to upgrade that. But when he was willing to fund it, then I had fun picking out parts and deciding what I wanted to build. Obviously, it was all with they call today white boxes, where you'd go and buy your own motherboard, your CPU, hard drives, and you kind of piece everything together. And I built my first computer myself, which was a good experience. And the types of friends I had were really into that as well. We'd talk about graphics cards and monitors and processors and what we wanted to get and how we'd update them.
I'm envisioning like Lil Rascals, Foster City, mid 80s, like Silicon Valley youth gang, making their own machines.
Yep.
It sounds like a dream childhood, honestly.
That's really dope.
Yep. And of course, we'd swap around floppy disks with different programs or games on them. And then once everyone, my first friend got a modem, that was a game changer too.
Oh, yeah.
Yeah.
We'd dial into different BBSs and, you'd get programs or whatever it was.
All right, don't flip out of it.
I know what a BBS
okay,
is.
I
knew it was coming, and like
again, it's a generational thing. It's not a condemnation. But did you ever use a BBS?
okay, so I know what they are, but no, it's almost like how I have the IBM Basic manual.
Okay.
But like it wasn't my manual.
So it is a reasonable question to ask you what a BBS is.
Yes.
Now, Steve, you and I are roughly the same vintage, but I think you were probably too cool to be using BBSs.
I don't know about too cool, but was not using BBSs.
Yeah, Steve was too cool, which is good. I mean, that's a compliment. That's praise. So you are. So tell us about the machine that you that early machine that you pulled the motherboard for and everything else.
Yeah, it was a Pentium 100 megahertz. I think I had maybe 8 megabytes of RAM on it, which was a lot in the days. Maybe a couple hundred megabytes on the hard drive. Don't quite remember then. But yeah, eventually installed a modem in that guy too, and started dialing in and playing different online games with my friends too. Well, online wasn't quite the word. It was point to point. So
right.
You would dial their home and their computer would pick up, and then you'd play your multiplayer game that way.
Yeah, that's cool.
And multiplayer. So this is now, we got to be in the early 90s at this point. Is that?
Yep.
With 100 megahertz. You can always date someone from their clock speed. Right?
I think I got that in 95.
95, right?
Uh-huh.
Yeah, something like that.
Yep.
Okay, so the internet is beginning to happen.
Yep.
And so you're actually able to do some interesting things online. Cool. Sorry. So then you head off to school.
Yep. Went to UCSB, studied electrical and computer engineering. Again, it was good as far as developing good social relationships with other hardware geeks like myself. And that's primarily what we did is we had something called the LAN at the time in the dorms, and you could
you repeat that word?
Just a LAN, local
LAN.
area network.
He's saying this because I like to call it lawn.
So Jess calls it a lawn.
Okay, but it's only patrol.
Can we describe
so
the
you're doing
look
it on
that Amir
purpose.
just gave you?
Yeah.
I know, I saw it.
I did not read this. That is troubling.
Yeah, it is like when you say you like to call it a lawn, it is a LAN. Like
It is a LAN. It is a LAN. Okay, I will admit that, but I do like to say lawn because it makes the cringy look.
I just cringed again.
It's very cringy. I think those cringes are social cues that you should stop doing it. All right. Anyway, so Amir, I'm so sorry. You never know you're going to step on a landmine around here in the
Or a
outside
lawn
garage. All right. So yes, you're on the LAN.
Yep. Made it even easier to share files and being even more geeky with your friends. Obviously back then you were doing a lot of things like running wares, where you would share programs that maybe you weren't supposed to be sharing with your friends. And, you had corporations who paid for software, but almost no one else did pay for software back then.
You're raising a kind of an important point about the role of mischief because I think certainly when I look back, mischief played an important, and if it was phone freaking or if it was kind of wares sharing, and as a parent, like I want to discourage mischief.
Oh yeah.
But as a kid, like mischief was an important part for and you're talking about, scaring your mom when mischief plays an important role.
Yeah. That's how you learn. I mean, if you wanted to do cool things, you had to figure out, you didn't have money back then. You had to figure out how the technology worked and how to get it to work in your favor. CD burning was a big one too.
That's right.
Oh,
yeah. And now I'm not even going to ask for that one. Now I know.
No, I also know of wares.
Yeah.
I mean, I got in trouble for that a lot.
I can imagine.
Oh, I thought you were going to ask about CD burning.
That'd
That'd be tough if she didn't know that.
So you're messing around on the LAN and presumably doing things in software as well. I mean, doing both computer science and computer engineering. Or
yes, software started actually early. I think another hobby I had was radio controlled cars. I love them, and that's how I learned actually a lot of electronics too and mechanics. There wasn't much software, which was a problem because you'd want to race your friends, and how did you know who was faster? And so on my XT, that slow computer, I actually built a program that tracked the time of these cars going around this course, and you'd get lap times from them, and it would show you who was faster. And in the end of the race, it would tell you who did the most laps in the least amount of time. And I would drag my computer out to the field with some extension cords. And my friends would get our car set up, and then someone had to be behind the keyboard to key in
I was going to ask
the appropriate buttons when the car crossed the start-finish line. And so I wrote a program. I called it Race Master.
Race Master. That is such an 11-year-old name for a program.
Yeah, I wrote it in Turbo Pascal.
Oh, Turbo Pascal. You're close to a Turbo Pascal manual, I think. Off to your right somewhere, there's a Turbo Pascal manual. I've got such fond memories of Turbo Pascal.
Yep. And that was the first program I wrote. I was living in Israel at the time. My dad had relocated there for a job over at National Semiconductor. And I had a group of friends who liked to race cars and were geeks as well. And we wanted to be able to keep time. And so I said, my friend had taken a private class in Turbo Pascal programming. It was popular then for parents to get programming tutors for their middle school kids. Don't know why. And
that is awesome.
He had a book, and I said, can I just borrow the book? And taught myself how to program Turbo Pascal.
All right. Do you remember what version of Turbo Pascal?
No idea.
Are we talking like 5.5? Are we talking?
Don't remember.
All right. Turbo Pascal is amazing. It was then fast. This is Anders Hejlsberg, who
of TypeScript.
Yes, and of Microsoft fame. And Anders was at Borland where they did Turbo Pascal, and it was very fast on a PC AT or on a 386SX or on a 100 megahertz Pentium. We should get Turbo Pascal running today on a modern CPU. I mean, it would.
So what happened to it?
It would travel backwards in time. It was so fast. I think I don't know what happened to it. Where the actual artifact is.
I don't know.
But it was side note, there is a current player on the Golden State Warriors, Eric Pascal, and the nickname that people are trying to get to stick is Turbo Pascal.
Turbo Pascal. That is awesome.
That's good.
That would be amazing.
That is awesome. That is
fast.
trying to connect two demographics that I'm not sure.
In the Bay Area.
In the Bay Area, you could pull it off.
Yep.
God, Turbo Pascal. I'd go to a Warriors game just to watch Turbo Pascal play. Just to watch. That's great.
That's awesome.
So that was all right. So you're messing around with software with Turbo Pascal.
Yep. In school, I was somewhat disappointed. The first programming class that was on the curriculum was Fortran, and I was trying to figure out why in '97 they were teaching incoming freshmen Fortran, and I did eventually figure it out. The instructor we had many years before had written a book on Fortran, and likely needed to increase his book sales. So that was the first class we took.
Okay, so F77 or F90? Do you remember?
No.
Because I actually feel Fortran, there's still a lot of Fortran being written.
Yeah, no, people
I believe it.
definitely use Fortran.
Because they got these mathematical codes correct. Especially in the sciences, there is still, Fortran being written is maybe a bit strong. There's a lot of Fortran that's out there.
Maintained.
Why am I defending your teacher's terrible decision to teach you Fortran? I'm sorry, I don't want to be. So, all right, so you were being deprived with Fortran programming in high school or
in college. Yep.
In college. Okay, college, that is bad. I don't know why high school feels like it's less child abuse than college, but
yeah, maybe because the teacher had also been as part of the College of Engineering and the electrical engineering department, not necessarily computer science.
Uh-oh.
Perhaps thought it was a better lower level language. I'm not sure.
Yeah. No. All right. So you're getting a bad taste for software from Fortran.
Yeah. Luckily, it was only a quarter's worth, and then quickly moved on from there to more modern languages. Call it C, for example. Yeah.
Well, you were lucky you're doing C because I feel that is a time that is now, because now we're in the 2000s, right? Maybe the early 2000s. I feel like Java kind of displaced everything for a while there.
Incoming freshmen in computer science started with Java. The electrical and computer engineers started with Fortran and then C.
Fortran and then C. So I actually think you kind of got the better half of that deal. I
agree.
Fortran is a little bit of an annoying price to pay, but at least you got something that's closer to the metal with C.
Yeah. And I actually wrote some code for Facebook, I'd say probably in 2010 for Memcache. That was all in C. So that came in handy.
I was so hoping that was going to be Fortran. I was really, as soon as you went Facebook, I'm like, please let there be some Fortran on Facebook. But no, of course. Yeah, there you go. So it came in handy.
Yep.
But coming out of school, you were you're doing hardware effectively in school.
Yeah, graduated in 2001. Basically, did hardware. Built a 4-bit microprocessor as one of our final projects.
Oh, that's great. That is so much fun.
That was a tough one. I remember it was due basically the week before finals, and we had spent maybe 3 weeks in the lab on the 5th floor of the engineering building. You stare down from the engineering building at the beach below, and you had all the history majors and communication majors studying in quotes,
right,
on the beach.
Throwing frisbees
in the sand.
Yeah.
Yep. And we're up in the lab trying to finish this project, and we did finish it, and it worked.
See, the cruelty there is that they had windows. They shouldn't have had windows. If there were no windows, then you would have been just in a cell.
Yeah, it wouldn't have known anything about the reality outside.
No, right. I think most engineering campuses just have no windows. So, what was the 4-bit microprocessor? I mean, was that an FPGA that you were putting into, or what were you?
One portion was an FPGA. A lot of the glue logic was done in an FPGA, but the majority of it was just in discrete logic chips. So we had an ALU, we had some memory. We had shift registers, we had muxes. We built it on breadboards. Those are boards, plastic usually with lots of holes and conductors underneath. So you could put in a DIP package, a dual inline package, which is how a lot of microchips used to be packaged back then. Basically, a piece of plastic with these small conductors coming out of them that you would stick into these boards with holes in them, and it would conduct underneath, and then you take wires, or old like telephone wires, and then connect between the chips that way.
And then spent a lot of time with the logic analyzer on that project for sure.
Logic analyzer, oscilloscopes, voltmeters, everything. And so you would take this, and we had 3 breadboards worth. So think about maybe something that was, I don't know, maybe 18 inches by 12 inches of a big rat's nest of wires, which made it hard to debug. We started off very neat, but it was fairly complex. We had a lot of wires going everywhere.
And was it a group project or individual project?
Yeah, it was a group project, 3 of us. And you would write, then you came up with your own assembly code that would run the processor. And then you would program that into some EEPROM, which is, I guess, today you might think of EEPROM as Flash, perhaps. And your goal was to have it execute a certain series of its instructions. And that was actually fun because
it must have been glorious to get it all working.
Oh yeah, once it was working, you didn't want to sneeze on it because if one of the wires came loose, it would have been hard to figure out what happened. Right. And then you could adjust the clocks manually, and then basically you would turn it up to see how fast or how much you could overclock that little 4-bit processor.
And what did you get to?
I think we got it to about 8 megahertz.
That is great. That is great. What a project.
Yeah.
I've always fantasized about having a project where you build your own microprocessor, then you build your own operating system, you build your own computer. You have an entire systems curriculum where you build it all from the bottom. But because you learn so much about the way things work from that.
Oh yeah, you have to get into every little detail. Yeah, it's amazing. It was a fun project for sure. A good way to finish off the 4 years of undergraduate electrical engineering.
Yeah, and meanwhile, that history concentrator that was out there, throwing the frisbee around, they're wishing they understood the 4-bit microprocessor.
Why are you pointing at me when you say that?
I'm sure they are.
I'm just pointing off into the distance. I'm not pointing. First, Wisconsin was too cold for the frisbee ice.
At least with sweaters and sweatpants.
Exactly.
Yep. The best part was you called the project the BURP. The basic undergraduate RISC processor.
That
Whoa,
is
that is a good
BURP is good.
name. That's a good name.
the BURP is good. And all right. So then you are now into your career.
Not really. So I graduated in 2001. .com bubble had just exploded. And in the first part of my senior year, I had offers for jobs. I had interned at Cisco Systems for 2 years. HP wanted to interview me for a position in their AIO department, which was all-in-one printer, scanner, fax machine, whatever it was. And that was when I started my senior year, and things were great. And I said, look, I'm not going to decide where I'm going to work now. Let's talk towards the end of my year. Then January came around, everything had crashed.
Bottom falls out.
I'd called up.
Oh man.
Called a bunch of these companies and said, look, we're not hiring. We're actually laying off people. So I graduated without a job.
Isn't it? It's amazing to think about that
yeah.
time. I mean, I feel like this is like our role is like, and I think, Jess, this is too old for you, right? I mean, you were in 2001, you were not in the labor market, certainly.
No.
Yeah. So you don't know what it was like. I mean, I feel like Steve, you Amir and I, we're children of the Depression in this regard, explaining like, actually,
got there in late 99 and went to Dell in October 99 just to watch the bottom fall out.
Yeah. I mean, you got there when the times were still good for a few months.
Yeah.
I hired an undergraduate in 2001 and it had to be approved by the CEO. It was a huge deal to get a single undergraduate hired.
That's insane.
And it was bad. So you come out without a job.
Yeah. I had friends who graduated with a 4-year engineering degree and went to go work at Best Buy.
Whoa.
Yeah.
Whoa.
Yeah. That's how bad times were.
Job.
Yep. So I decided I didn't want to work at Best Buy. Instead, I spent a year volunteering. I did a program similar to Peace Corps in Israel, where you work both with Jewish and Muslim children on some coexistence programs. Largely, if you're an English speaker there, you're naturally going to be used for teaching English. And so I taught English for a year to kids in marginalized neighborhoods, both inside a Bedouin village. It was a lot of fun.
That is amazing.
That is an amazing experience.
I'm now embarrassed about the way that I and the rest of humanity spent that year, like wishing for the bubble to come back. Meanwhile, you're actually doing something meaningful.
Yeah,
that must have been
cursing the fact you could only get one undergrad.
Exactly. Exactly. I'm cursing the fact that must have been a hell of a year.
Yeah, a lot of fun. Came back from that, started a small little company. I made battery chargers for model airplanes. And they actually plugged into the parallel port of a PC and kept statistics on the batteries that you were charging.
Are your parents concerned for you at this point? It's like, Mom,
no.
Don't worry. I've got a plan. I know the economy has cratered and there's no future for engineering. I'm starting a company to recharge model planes.
Yep. I didn't know much back then. Didn't know how to size up markets.
Right.
I was like, this is a cool device.
TAM on that one?
Yeah, I'm going to use this because I love flying model planes. So I want this. Other people must want it too. I'm gonna do this. And my dad gave me a couple $1,000 to help build the first one.
God, good for Dad.
That's
great.
Yeah, it was awesome. Then I quickly found out. I think I sold 6 of them. And
you saturated the market.
Exactly, dominating the market.
Exactly. Didn't realize most of the people who flew these planes were retirees, and didn't see the need for using a computer to charge batteries. Right. Probably still the case today.
Plenty of time on their hands.
Yep. And so, I had a girlfriend at the time, and she, I'd started looking for a job, and she found an ad on Craigslist for a company that needed someone to help them repair servers. And I said, great, I can do that. Not a problem. And then I sent in my resume and I get a response, and the recruiter was from this company called Google.
Wow. And
I said, wow, the search engine, I guess they should have quite a bit of servers. Should be a lot of work to do there. The funny part is, first time I sent in my resume, I didn't get a response. I sent it in again. I don't remember why, but I updated it and I wrote some of the experience I had working with Linux the second time. And that got me a response from the recruiter.
Really? A 4-bit mic? It's like, I'm sorry, I implemented BURP. Like right. that doesn't wake you up, but like, okay, yeah. Like, and by the way, I know how to administer Linux. Like, oh, now we're interested. Okay.
Yep. So I went and interviewed and got the job there, and then was thrown immediately into the trenches. And there was almost a hazing there from the other data center technicians, where to be a part of that culture, they would give you a hard time over some of the work you did. I remember once I got yelled at by a senior technician because I put too much grease on the CPU.
Oh my God.
Thermal compound, yeah. And that was a hard one to get over. And, it's your first job and you take that seriously initially.
Well, okay, that is, do you know what he's talking about in terms of the thermal grease?
The grease? No.
No, okay, this is like, you should explain like the thermal grease, because you're actually connecting the CPU into the socket at that point.
Yep. This is actually something that will come back to bite me later on. But the CPU has a metal casing around it, and that interface is a heatsink, which dissipates the heat that the CPU generates. To make that connection between the metal case of the CPU and the heatsink more efficient, you can put a thermal compound, which is it conducts thermal energy from one material to the next, and it creates a better connection between the CPU and the heatsink itself. It makes the cooling more efficient. And you can put too much. If that layer is too thick, it doesn't conduct heat as well. If it's just right, it conducts heat really well. And so I put too much, and that barrier between the CPU and the heatsink was not as efficient as a result.
Oh, wow.
And it would have worked fine, but someone was looking for something to pick at, right? And
yeah.
Was it more than an aesthetic issue? Because there's an aesthetic issue too if you put too much on, right? I mean, I do not have the guts to do this myself.
It seeps out the side. It's not a big deal.
Yeah, it seeps out the side, but it's okay, not a big deal. But there's an actual efficiency consequence.
Yeah. You won't conduct as much heat, and then your fans need to spin up to compensate.
Wow. And in 2002, is that the year at this point? 2002, 2003?
Yep, it started in 2002.
In 2002, in the Google data center, this is a newbie mistake, I guess.
Yep.
So then the hazing begins. One day in the hot aisle, one day in the cold aisle.
Yeah, it lasted about 3 months.
How long have you been sitting on that one?
Yeah, but eventually you get past that, and you're no longer the new guy. And at that point, things get easier, and then you're training other people. And that was an interesting time. We couldn't get racks into data centers fast enough. And it was expansion. So it changed quickly from repairing the fleet that they had to building out more and more clusters of servers.
And this is after the Velcro days, right? Or is this,
there was still Velcro then.
There's still Velcro.
Yep.
So do you know about the Velcro?
Yeah.
Do you guys know about the Velcro?
No.
You should explain the Velcro, because the Velcro is definitely a big part of Google lore for sure, right?
Oh, for sure. If you think about hardware back then and scale out servers, they didn't really exist. You could buy rack mount servers. They weren't at all cost effective. And even from the founders, from Larry and Sergey, they had decided that they weren't going to pay the enterprise premium on servers. And a lot of the initial Google servers were built from components which they had purchased from a local hardware retailer called Frazelle Electronics. They would go there.
Oh, Fries.
Wow.
Oh, Fries.
That's going to become a thing of the past too.
It is.
Oh, it's there.
It is. It's a carcass right now. And that's sad.
And they would buy 20 motherboards and CPUs and drives and DRAM, put them together and put them on what they called cork boards. And if you think about, there was something before that too. You think about a bread rack at a bakery. They have these tall racks that you can slide basically pans into and bake bread in volume. So they took that concept and said, look, we're going to use that same idea to hold servers. And we're not going to buy traditional 19-inch racks. And we're just going to build these very inexpensive bread racks and have a tray and then snap the motherboards on there and the CPUs and put some DRAM, some drives, and some fans. And that will be our server. And those were largely built from commodity components that you could buy at Fry's.
I mean, true, not just commodity, but consumer grade.
Consumer, yeah.
Yeah, I mean, this is
gigabyte motherboards, whatever was there. The initial versions had a layer of cork between the metal rack and the motherboard in order to insulate it so it wouldn't conduct. And that worked fine, except for the inspector, the fire marshal who would come by the data center, saw the cork, and it was a flammable material which you weren't allowed to have out on the data center floor. And so eventually they had to get rid of the cork. And so the cork boards were phased out, and they had these things called bread racks instead that held the motherboards on standoffs instead. So that solved that problem. But there was this ongoing evolution of very inexpensive consumer hardware being brought into data centers and being used for enterprises, for an enterprise application. Call it a scale-out application at the time. And that was really the first version of scale-out hardware that I think started at Google. It was super cheap. The joke was they would buy DRAM that was swept off the floor at the factory because it was cheaper and it had more errors. But if you wrote good software that could take into account the errors, it would be cheaper, right? And so you couldn't. The premise was you couldn't rely on the hardware. The software had to accommodate that, but as a result, you get cheaper hardware.
So this is non-ECC DRAM.
Oh no, non-ECC.
Bad non-ECC DRAM.
Yeah, no error correction at all.
There's only so much that software can do. For Byzantine DRAM, that can be a challenge.
Yeah, if it caused a kernel panic or something, that's fine because the software could just use another server instead.
Yeah, just don't bother debugging that one. That one will be strange.
That was the debug process was very crude, and you would just en masse rip out components and replace them until you found the combination that worked. And you would throw...
It's a real first principles kind of operation there.
You would throw a lot of good components into the RMA, into the return bin.
Right.
I'm sure the false positives on bad hardware was probably very large at that point.
Right. I mean, it truly is penny wise and pound foolish. I mean, you're actually... so in the Velcro, does the Velcro predate the cork or postdate the cork?
That's right. We started with Velcro. No, Velcro was from the beginning in the cork boards and in the bread racks. And basically, you needed a way to hold these hard drives in place. And they would just have a simple mount for the drive, and you would just use a strap of Velcro to tie it into place. The interesting thing, the whole premise of that was that you wanted to make this server, they had so many of them, easy to maintain. Right? You had armies of data center techs trying to fix unreliable hardware. So you had lots of failures. And if you could save a few minutes on the maintenance, it was a win-win. And so they made everything really easy for the technicians to maintain, to rip components in and out. And the Velcro was a key component of that.
But the Velcro did not survive.
Yes, it did not survive. At some point, they became more serious about the hardware.
Right.
And they started using ECC and the principle of easy maintenance remained. They found other solutions that still made the service just as easy, but just happened to not have Velcro.
All right, we're going to take a quick break. Then we are going to be right back with some terrific tales from the hardware software interface with Amir Michael. On the Metal is brought to you by the Oxide Computer Company, where we're going to try a new feature shamelessly ripped off of Reply All's Yes, Yes, No, where our boss, Steve Tuck, brings us a tweet he does not understand, and Jess and I try to explain it to him. Steve, do you have a tweet?
I sure do.
Go for it.
The tweet in question: UEFI pre-boot network stack engaged the onboard NIC in such a way that it would write back DMA to particular physical memory pages sometime after control was passed to the bootloader. Corruption would occur somewhere in the user parts of the RAM disk. No idea.
No idea. Jess, do you understand this tweet?
So I understand definitely the part about the UEFI pre-boot networking stack, but the part about DMA is in question marks. So it's like, I guess you're not really sure where that's going.
You're overthinking it. I understand this tweet. Running on-prem is painful. This is dealing with an awful firmware bug. The firmware has overwritten part of the operating system in a way that is extremely painful to debug.
So who do you go to in that case?
Who do you go to?
You definitely strangle one of your vendors.
You strangle one of your vendors, and unfortunately, your vendor is a PC vendor because all of the existing computer companies are selling personal computers. What we need is a new computer company.
So this is just saying I'm in intense pain trying to run systems on premises.
That's exactly what it's saying. Steve, what can someone do if they're in intense pain running on premises?
Well, if someone is running in intense pain on premises, what they should do is go over to oxide.computer to learn a little bit more about how we are going to take that pain away.
Help is on the way. Join us at oxide.computer.
You are not alone.
All right, we're back. All right, so Amir, we were with you at Google, and Google is beginning to realized that having junk components everywhere might not be the best long-term approach.
Yeah, there was some change in philosophy around that. And I think at some point, the supply chain perhaps drove a lot of that when they started negotiating for hardware directly with the actual vendors. They realized that they could get, there just wasn't enough DRAM on the floor of the factory that they could get.
There's not enough bad DRAM to sell you.
The scale had grown so much, right? And so you had to work with the vendors directly, meaning you had to be a little bit more grown up at that point.
It's like we have to buy legit DRAM because there's not enough bad DRAM. That's pretty funny.
There was that, and quite frankly, the hardware and the designs had started to show some weak points too. Not a lot of time was put into the engineering behind it. So for example, we had servers that were overcooled, meaning we were running too much air through them, which made the facility run less efficiently. The power supplies, for example, that we wanted to use, we wanted to increase efficiency on them. And so you had to start doing custom designs at that point.
Interesting.
Everything had sort of matured. And along with the supply chain, along with the designs. And so when you're at that scale, you're going to spend more time on the design so that you have less risk involved. If you made a mistake early on, it wasn't that bad because you didn't have that much hardware. But if you're deploying tens of thousands of servers and there's a bug, that's a fairly expensive mistake at that point.
And so you had come into Google as kind of a data center tech answering a Craigslist ad.
Yep.
But at this point, it sounds like you're moving on to the design side.
Yes. So after around 9 months to a year of traveling, debugging servers, deploying new servers in the data centers, they started becoming more serious around the hardware design. And that's really what I wanted to spend my time on. And a lot of the work that they were focusing on was around efficiency. They saw big inefficiencies in how traditional servers and data centers worked at scale together. And a lot of the ideas were around combining the two, the facility, the actual building, the power distribution, the cooling in the building, and the servers. And that's a really important principle. That's actually what I brought forward into Open Compute as well, which happened later on in my career. But when you can control both the facility and the server, you can do fairly amazing things as far as efficiency goes.
So really not just rack scale design, but really at that point even thinking about data center scale design.
Yeah, they called it warehouse computing at the time.
Oh yeah, nice. That's like the book from RISC.
Yep. That's where it came from.
Yeah. But that thinking was really very early then. So that's in 2005. It sounds like. Is that?
Maybe even somewhere earlier. Around 2004. I remember we had a number of different brainstorming sessions. I got to participate in a few of them over how they're going to make this holistic design way more efficient. And they looked at things as far as putting micro turbines on the roof to generate electricity, around different types of cooling systems, backup solutions. The container was an interesting one as well, the shipping containers. And the first sort of custom server facility that they wanted to put together was in a shipping container. And so that was about a year that we spent on with optimized cooling, optimized power distribution.
In the shipping container.
It's so cool. That shipping container is in the Google New York office and you can have meetings in it. It was my favorite spot.
Well, so I wonder if that was, so Sun had this thing called Operation or Project Blackbox.
Yep.
That was a bunch of compute in a shipping
Everybody
container.
had a shipping container at one point.
Yep.
All right, listen, I find
it was a hot thing.
It was
that
nothing,
was a run.
It was nothing special. I heard that I was never inside it when it was operating. The airflow that you have to get inside the shipping container, it's like a tornado inside the shipping container.
Whoa.
In order to keep things cooled was a shipping container is not a great place to put a data center, was kind of my read on it. Is that a fair assessment or no?
It is in some ways a very good place. There are some operational things that make it a challenge. And we were watching other containers as well. We were ahead of them, I think, by around 6 months to a year. The principles that went into that were really important. It's power that had to travel a short distance. It's a very short loop for your cooling air. The further you have to move air, the more energy you're going to spend. The container made that loop very short. And so you spent a lot less energy on moving air. it made everything in a nice tight package that we thought would be useful for quickly deploying infrastructure at the time. And shipping containers are cheap. I think at the time we bought an old container for $2,000 or $3,000. Fabrication was fairly expensive. There was a vendor who did a lot of the fabrication, drilling holes in the side, putting up a unistrut, which is a metal bracing that was used to hold up a lot of the racks and things like that inside. We had to do a custom cooling system with control algorithms for the fans, valves, controlling how much water went in and out of the container. The first version had 1,200 servers in it, so it was fairly dense.
Yeah,
small package.
That is dense.
Yeah, it was downstairs in the garage, in the Google garage. At that point, they were at the campus in Mountain View, the old SGI buildings.
Yeah, right.
And so we lifted up some grates and we got a big crane and it dropped the container down into the garage. And then we put tarps on top so you couldn't see it from above. And we surrounded it with a cage, a fence, and had a security guard in front. And in the winter, it dripped, rain would drip on top of it. And we had a table outside that would get wet from the rain. But we did a lot. That was a good learning experience. And Google did eventually deploy tens of those into a data center into Atlanta. And the important part were the principles. So the efficient cooling, the efficient power distribution, the lack of a UPS or uninterruptible power supply, a traditional system that you had in the data center was in the container. All the servers had their own local batteries on them too. And there's a lot of learning. You learned what not to do. You learned how to make things more efficient. Ultimately, it was the sort of the platform that carried forward into their next generation designs.
But so why do we not have shipping container based DCs today? I mean, what were the problems with the form factor?
The idea behind it was that you could put it down anywhere that had power and water, right? And some of the initial concepts had them out laying in fields. Right. And you would just run a spine of power and water and plug these containers into them. That didn't sit too well with some of the management, and they were concerned about security, and they wanted to put them inside of a warehouse. So you're building another shell around your existing container, and you've in a sense built two roofs around them. Also, moving them inside of that warehouse was challenging.
Right.
There was a custom crane system that was built to move the containers, and it ended up being overall more expensive. You also needed redundant fire suppression, both in the container and in the warehouse too.
Interesting.
So the cost actually went up.
So it's nothing about the form factor per se, and if you wanted to drop it into a field, it would have been fine. Because I always assumed that there was something about the actual physical form factor that made that a non-starter. Because a bunch of folks investigated it kind of at the same time and all came to the same conclusion. But it sounds like it's got nothing to do with it. It's management.
Yeah. It's more around the facility cost around it, which ended up being too high. And we looked at it and said, look, lots of great engineering principles here. Let's take those, but let's just do them in a standard warehouse or it wasn't really a standard data center, but in a data center, what we'll call a data center.
Interesting.
So we took out the shell of the container, but kept almost everything else.
Kept that interesting. And so what year is it now? Are we now 2007 maybe?
Yeah, probably around there. Yep.
And you learned a lot from the container experience.
Yep.
And now we're beginning to take out the shell of the container and just taking it by the rack effectively.
Yep.
Into DCs. And so yeah, what was the education from that? I mean, it sounds like that approach is obviously working at that point. Right.
So bringing the water as close as you can to the loads so you can minimize the distance of the air travel to cool the servers, getting rid of building-wide UPS systems so that you can have localized UPSs on every server. Just overall, how do you design a more thermally efficient system running with as few power conversions as possible? In a traditional data center, you have high voltage coming in to a medium voltage transformer outside the building, and then smaller transformers inside the building feeding each server. And so can you take out some of those, and then you'd have your traditional UPS system, right? Doing a AC to DC, DC to AC conversion. Can you take out as many of those conversions? So everyone, you might lose 5%, but if you can get rid of those conversions, you can be even more efficient. So that was part of the learning. serviceability. How do you deploy them quickly in data centers? How do you repair them quickly? All those were the main learnings from that project.
And were you engaged at all with the kind of traditional vendors in the space? Because the tragedy is that, today, if I go buy a machine from an extant company, it doesn't have any of that education in it for doing the power. You've got all these different power conversions and everything else. Had you already come to the conclusion that the existing vendors were not going to really?
Yeah, the existing vendors were never really if you think of traditional server vendors, were never really a part of the story at Google, because it had started from home-built hardware or in-house built hardware. Those vendors were never really a part of the conversation.
They just weren't present. Yeah,
they went straight to the vendors that were willing to do custom work for them.
Interesting.
Which typically meant going straight to Taiwan.
Yeah. And then, so about this time, when do you go to Facebook? About this time?
Or 2009.
2009. Okay.
Yep.
And so what is the Facebook that you arrive at? What are they running at that point?
So they were working with traditional vendors at the time, and they were in co-locations, so a shared data center. They had a few facilities that they had occupied themselves entirely, but were still leasing them from vendors, traditional data center vendors like Digital Realty Trust or whoever it was. And what was similar was the growth curve. So they had projections around how much infrastructure they would need, and it appeared to be very large. And the cost of that was a challenge going down the traditional route. And it was, and I credit the leadership a lot at Facebook at this time. They said, look, we need something more cost efficient. Come in and figure it out. What do we need to do? How do we reduce the price so that we can continue to scale Facebook with while still maintaining a business that allows us that we can operate without paying so much for the infrastructure itself? And I was there. There was another engineer who had done a lot of work on data center design and construction before, Jay Park. And we basically sat together for 6 months and said, look, if we can start from scratch, what would we build? How would we do this integration of the server and the facility again? And what do we know not to do? And we spent 6 months coming up with ideas. I came up with slide decks and projections around what efficiency savings would be, both on energy consumption, on cost, and presented that to leadership. And they said, that's great. You guys want to, the proposal was to do everything from scratch, right? And so you come to them and you say, hey, we'd like to just do a whole new server and building design. If it doesn't work, we'll be in a lot of trouble because we need this capacity. And we've also, breaking ground on a facility isn't a cheap proposal. You're talking, $200 million project. And if it doesn't work, you're out of luck. But they said, okay, we trust you guys. Go ahead and try to make this big bet work for us.
There must have been a moment where you're like, oh shit, they bought it. I just think back to times in my career, you make some big audacious proposal. Yep. And you kind of you're so focused on making that proposal, you don't really think about like, oh my God, what if they buy it?
Yeah.
They bought it.
They bought it. And that feeling stayed with me for the next year and a half as we're actually building it.
Oh my God.
It was never I could never take my foot off the gas pedal, because what if it didn't work in the end?
Right.
And it was a big bet, and they were willing to take big bets. And
how many people were involved at that point?
So we'd expanded the team. I think by the time we had launched or went to production with the first set of servers in the custom facility, there were probably 10 people on the hardware team, and probably a similar number on the data center facility team.
And surely some things went very wrong en route.
Things did go wrong along the way. Every single one of the things we were able to overcome them.
Right, of course.
But
there must have been something memorable though.
A lot of luck that when we actually went in there and we called them the Marines, the first 1,000 or so servers, and powered them on, they actually worked. I'm sure a lot of luck was involved, but we did have some very hairy moments where we thought everything was not going to work.
All right, so take us through. There's got to be a hairy moment that we love. The hairy moments.
Best ones.
Yeah.
Yep. There's a couple. Well, so we did a lot of very aggressive things with the design. Part of that was a custom motherboard, and when you're doing a custom motherboard, basically everything we did was custom, from the power supply, even the power strip was custom. But this motherboard was interesting. We picked a completely different form factor, 13 by 13 inches, that wasn't industry standard. And we were lining up with Intel's Hejlsberg processor, which was the first time Intel had connected the DRAM directly to the CPU.
Right.
Typically, it went through a Northbridge, another chip. This was the first time they connected the DRAM directly to the CPU.
And that's via QPI, is that right?
Not QPI. QPI was inter-processor communication. This was a standard DRAM interface.
Okay.
Yep. And so they did that, and we had brought up a couple boards, and we did our PVT, our production verification tests, which is when you have several hundred systems and you're making sure that you don't have bugs at a larger scale, right? There are things that get by in earlier phases of development, like EVT or DVT, which are the first two phases of test, and they're smaller volumes, so you may not see bugs that crop up on only 2% of the servers. But if 2% of the servers have a bug, that's a big deal. And so in PVT, we came across this bug where we would boot the boxes and half the memory was missing. And this is on several hundred systems, and we're trying to figure out exactly what it is that's going on. And
so the operating system is booting normally. Everything is fine.
It'll boot.
It's just only seeing half the DRAM that's physically in the box.
Yep.
Okay.
Yep. A couple DIMMs would just go missing. Yep. They would physically be in there, but just wouldn't recognize them. What made this so challenging was that we had a deadline that we needed to approve the motherboard design in order to hit our mass production date. And it was only about a week away. So we needed to figure out this bug as soon as we could. And we basically all went down into a mode where everyone just focused on this one particular bug. And there were long nights in the data center with a lot of smoke breaks outside in between.
And is it reproducible? Once one machine only sees half the DRAM, will that machine only see half the DRAM? Or does a power reset change what it sees?
It was intermittent. So sometimes it would come back, sometimes it wouldn't. It happened on a very small percentage of machines. So every time it happened, we would try and capture what was going on. We had excellent partners who were helping us out. So Quanta, who was doing the motherboard design, and Intel, whose platform it was based on, all went in with us, and they were working a lot with us too.
So you have them at least somewhat convinced that this might be their problem.
Yes, we didn't take any convincing. Everyone wanted us to succeed, and they said, look, if there's a problem, we're going to jump in and help you.
Oh, that's great.
So it was great. Eventually, we roped in the DRAM manufacturers as well.
Oh, wow.
And you know, it took a lot of engineering resources. Eventually, what we found out was that there's the DRAM, when it starts up, the BIOS takes it through a training portion, and it tests the DRAM, and it does different tests to understand at what speed it can clock the DRAM at. And that procedure, I'll just tell you what the problem was causing some vendors' DRAM to go into a debug mode. So the bit banging.
So the actual DRAM, the training of the DIMM was causing the DIMM to go in. It's exactly the opposite of training.
Exactly. And so the DRAM manufacturer didn't necessarily, there's a device on there called an SPD on the DRAM that is responsible for setting clock speeds and everything else, went into this training mode, and as a result, it didn't initialize the DRAM properly, and the BIOS said, well, there must not be any DRAM there, and then the DRAM disappeared.
Wow. And now that's software that's doing the training. That is just that's very proprietary software historically.
Yes.
Did you guys have access to that, or
we did not have access to the actual code, but Intel did, who had written it, was helping us debug it. And together with the DRAM vendor, they figured this out after lots of probing of logic signals and things like that. Made a quick change to the DRAM, and problem went away.
And so was that a software change then to make it?
I can't recall if they actually changed the SPD on the DRAM or if they changed the training to accommodate for that defect in the DRAM. Yep. But before we had solved it, I got a call. I remember it was a Friday night. I was at a family dinner, and the vendor, Quanta, called and said, look, we need to make a call. Are we going to move forward with manufacturing or not? And I needed to decide, together with my team, if we felt confident we'd find a solution or not. If we
Is
said
this a hardware problem or a software problem is effectively what they're asking you, right?
exactly, do we go forward with manufacturing thousands of these boards, knowing we may have to rework them later on, or perhaps trash them even, or are we confident we're going to find a solution?
Wow.
And so the deadline had actually come before we'd found the solution. And so we decided to go forward with production. And luckily...
You were all in. This can be fixed in software.
Yep. And it worked. And everything from there was relatively smooth sailing.
Wow.
That's cool.
Yeah.
Taking a page out of your Google days.
Exactly.
Well, and we talk about bugs at the hardware-software interface a lot, but that's an exciting one because you're having to make a bet that whatever this defect is, we'll be able to work around it effectively without pulping the hardware.
Correct. Yep.
That's fucking crazy.
Yeah, and hardware engineers, I'm sure, go through this quite often. You don't hear about the stories often.
Right, you really don't. Yeah.
But it wasn't the last time that happened.
Yeah, and from a software perspective, we are not often at that point of actionability where it's just like, no, this hardware's already broken. Like, figure out a way to deal with it. So it's like, all right, we're just going to have to work around it in some way. But to actually be at that decision point must have been very anxiety producing.
Yeah, I mean, there was a lot on the line.
Right. Well, good for you. You boy, that must have been a great sense of relief when that was found.
Good choice.
It was. And the actual first deployment we didn't call them OCP servers at the time. It was called Project Freedom because we wanted freedom to do our own designs. Other people had taken that and interpreted that as freedom to escape from Dell and HP, which were our vendors.
Yeah.
That's not why we called it Project Freedom. We wanted the freedom to do our own designs. And
aren't those aren't the same thing? I mean, aren't they a little bit the same thing? I mean, I'm not don't want to pick it that way. So okay.
Not necessarily. I mean, we were looking for good vendors who could work with us. It had traditional vendors stepped up and said, look, we like your designs. We'll build them for you. That would have been fine too. We didn't have a bias around who would have worked with us at the time. We ended up going with vendors we thought would be most flexible to deliver what it was we asked for.
I'm not saying I don't want to be your child anymore. I'm just saying I don't want to live at home.
You could say that, or you should remodel your home if you'd like us to continue living here.
There you go. Exactly.
Yep.
But it sounds like no remodel was forthcoming, or
there were. They came a little bit late. We needed to have a contingency plan. So we had built this custom facility that couldn't work with a standard 19-inch server any longer. It didn't have a UPS system. And there were vendors who had rack-level UPSs at the time, and we had built up a contingency plan with them to use our custom motherboards inside of their own racks.
So could you talk about the rack width a little bit? Because the 19-inch rack obviously dates back to whatever.
Old telco days.
Days.
Yep.
Yeah, and dates back to the railroads, right? I mean, it's a super dated notion. I guess that's false.
That's false.
That's false. We've been over this.
That's an internet falsehood.
That's like a Snopes.
You keep
confirmed
perpetrating
false.
it, though.
I keep perpetrating. But the point is, it's a very old idea, the 19-inch rack.
Right.
And it sounds like you guys put everything on the table. What did you come with in terms of the rack width? I mean,
the first rack design was a 3-column rack. So a lot of the principles that drove the efficiencies came from marginal gains. And a lot of those marginal gains came from amortizing cost of infrastructure across more servers. So if you can have a rack and instead of putting 40 servers in it, you could put, say, 120 servers in it. That cost of that rack is amortized across more boxes. Everything becomes cheaper at that point. So we said, let's put 3 columns of servers together and roll them in. The cost of the rack went up, but we had more servers. And so the actual cost per server went down of the rack. It also made it faster to deploy. You're deploying 3 columns at a time instead of just 1 at a time.
And why 3? Why not 2 or 4? Was it just that was where the sweet spot was?
Yeah, we looked at how you'd line them up in the aisles of the data center. 3 made sense. A lot of it had to do with our backup system, which was a single column of lead acid batteries. And we thought we had enough capacity in that localized UPS in that column of lead acid batteries to maintain power to 3 columns of servers on one side and then another 3 columns of servers on the other side. So 6 servers. So we would sandwich a stack of batteries between 3 columns of servers. Yeah.
Interesting.
A lot of it came down to network ports too. How do you use all the network ports on a switch and amortize the cost of the switch across more servers.
Got it.
So three made sense.
Three made sense there too. Yep. And so, and then does the width then come from that?
The width we decided could be arbitrary.
Okay.
We said, let's do what makes sense and not try and fit it into any constraint that was defined by the facility.
Got it.
Yep. And so that was a interesting design because the weight also went up. So
right.
Packaging became a challenge and shipping them became a challenge. Not so much with compute servers because they didn't have hard drives in them,
right?
Which meant they didn't weigh too much. But in some of our initial calculations around doing a storage server and filling up, we called it a triplet, a triplet rack with hard drives, you were looking at the weight of a rack that was almost equivalent to a large SUV.
Right.
And pushing an SUV down your data center floor didn't seem like a good idea.
Well, you also have issues, right, where you're, depending on how you are going to load those spindles and how high they're going to be, you end up with a lot of weight potentially high up in the rack that it can be, you end up with a lever, basically. You can end up with the rack tipping over.
Right. You'd put your heavier weights towards the bottom so you'd get a lower center of gravity.
Right.
It is a consideration.
It's a consideration, right?
More so of how do you remove that off of a shipping truck onto a loading dock, and then from the loading dock into your data center. Sure.
That is real systems thinking. I have to think of like really end to end about kind of all those different steps.
Yep.
Wow. So did you end up making the rack a bit smaller as a result of that?
Yeah. So the second generation rack, which was the open rack, which came after the triplet, was built on a single column, and that lent itself better for storage servers. It increased the cost of the rack per server more, but that was a trade-off you had to make.
And is that the rack we have today, that 600 millimeter rack? Does that come from that?
That form factor came from that.
That form factor, yeah, right.
They're onto different versions of open rack. There's V2 and whatnot, but it came from that.
It seems like the width has stayed somewhat constant over the...
Yeah, at some point, the data centers are built around floor tiles, which are, I believe, 24 by 24 inches. And so you want a rack to take up 2 floor tiles because then you can put them in standard data centers. And that was something that, when we first started OCP, we said, doesn't matter what kind of floor tiles you're going to have. We're not going to have floor tiles in our data centers. They're going to be on concrete floors. Therefore, you can go for any sort of width you want. And once we had realized that there were benefits to allow deployments in traditional data centers, we moved back to the standard floor tile width for the rack. And that made it easier for other people to adopt OCP or our designs as well.
Interesting. All right, so we're going to take another quick break, and we'll be back with Amir Michael on the metal.
On the Metal is brought to you by the Oxide Computer Company. Well, bad news. I just got back from a meeting with the attorneys.
Oh boy.
They are not going to let us say much in these ads. We can't talk about the customer experience today for on-premises infrastructure.
So we can't do my idea to be like, are you being gaslit by your vendors? Because that's what they're doing. They're gaslighting people into thinking that these bugs only exist on one of their machines when it exists on like everyone's.
God, no. They called that, I think, quote, a third rail.
They must be following Jess on Twitter. I knew that was a bad idea to let the lawyers follow Jess on Twitter.
They also said we can't talk about public cloud customer experience.
Oh, come on. We can't talk about the rapacious bandwidth pricing? I mean, it's practically criminal.
No, can't talk about the unit economics of that at all.
Can we use the word criminal with respect to public cloud vendors?
Definitely not.
Oh, boy. What can we do?
Well, they did say, they gave us a statement we can use, which is...
Are you going to read from it?
Oxide Computer Company is building something that should help some people.
Well, that seems very direct. Come on. Can we at least send them over to oxide.computer?
We can. The other bit of bad news is all the lawyers were there in the meeting.
Oh, wait a minute. Not just the cheap one, but the expensive one?
Yeah, they were all there.
So we paid a fortune to get this terrible ad. Oh my God. Please, listener, go to oxide.computer and learn what we're actually doing. All right, we're back. So we were talking a little bit about OCP and the Open Compute Project. How did that get going?
That was... a result of the effort. So Project Freedom was the name of the first custom design. We looked at that and said, wow, that's great savings. I think it was 38% more energy efficient, 24% more cost efficient. And there was an idea that other people should have access to that as well. And if you thought about Facebook's business model, it wasn't at all based on their ability to deploy efficient infrastructure. It was based on a social network. The two things were completely different. As a matter of fact, the social network was built on many open source technologies that Facebook was able to benefit from and deploy in their own infrastructure, like Memcache, like MySQL. And so why should we keep this amazing innovation for ourselves? Because it's not our competitive advantage. Let's let everyone have those same efficiencies. It's better for the next generation of companies. It's better for the environment. You're using less energy. And so we said, great, let's open source this.
I feel this is something that gets a little bit misinterpreted out there, because I think people treat Facebook's inception of the OCP pretty cynically as like, oh, they're just trying to make their own gear cheaper or what have you. But my read on it is that just exactly what you said, that there's a very earnest desire to give back this important innovation.
That was the primary driver. There was always an idea that if other people adopted, volumes go up, prices go down. That was maybe 10th on the list.
Interesting.
Other things there were collaboration. Hey, maybe we don't need to engineer everything. If other people adopt, we can work together with them, build the next generation together, and creating collaboration across engineers is always interesting. It makes you an attractive employer, right? Engineers like to work on projects that are out in the open, right? You can hire an engineer easier if you tell them, well, you're going to work on this public project and you're going to be able to drive it. That's always another benefit too.
It is a benefit, yeah, isn't it? Yeah, and I think maybe everyone's got different motivations for that. I'm sure some of the motivation for that is I want to be people to see the work that I do.
But also it has more of an impact. I mean, it has impact outside just the company that you're working at.
Was there selling you had to do internally? Were there folks that were concerned about opening it up?
Surprisingly enough, there was very little resistance internally. Everyone just got on board and said, this is the right thing.
Makes sense.
This is the right thing to do.
Great.
Legal, obviously, we needed to give us the sign off, but even that wasn't there was some hesitation, but even that went fairly smoothly with them. There was more, call it challenges trying to figure out what to call the project than it was if we should actually do it or not.
What were some of the other names?
I don't remember any of them specifically, but we couldn't decide within the immediate team that was running the project. And I think, someone was having a chat with Mark Zuckerberg about the name, and he said, well, you should just call it the Open Compute Project. And it came back.
There's a reason he's the boss. I mean, that makes sense. It's a good name.
Yeah. And that's really where the name came from.
Yeah. It's a good name. It's definitely a good name. And I think I would love to know what some of the dustbin names were, but that's a good one. And then that is now, are we 2011? Is that right?
That was 2011. Correct. Yeah. In April 2011 is where they did the public launch of the project.
Right. And I remember, that it turned a lot of heads, and the vision was great, but it's just slow going to get people kind of bought into it is my read on it.
Yeah. A lot different than an open source software project,
right,
which you can just download and start using. This is hardware. It moves slower. People have existing solutions. A big part of it is the ecosystem. So who am I going to buy from? Who's going to support it? That doesn't really exist as much in software today. And so I remember the first OCP summit we did had, a couple hundred people there. And it was largely vendors too, who wanted to come by and see what Facebook was up to. There were more progressive companies who ran large infrastructures, some banks. Rackspace was one of them too, who said, look, we buy a lot of this stuff. We don't have the resources to do our own custom design. Let's work together. And we sort of latched on to a lot of those partners too. And from there, it just slowly started to grow. And the second summit was, maybe a little bit bigger, and then the third a little bit bigger. And then eventually other large infrastructure companies, I'm talking, some of the mega scalers like Microsoft and Google said, hey, this is actually a good thing. We need to take a lot of these principles and do them on our own designs. Let's start working together.
And for those who haven't been to OCP Summit, I think Steve, Jess, and I can all recommend it. It's
super fun.
It was fun. The technical communities there are really great. I think that we walked into some of those breakout rooms, and they're just great. The vibe was great. It was people.
It's big. Very well attended.
Yeah, it's fun, and it's got a lot of neat hardware on the floor, and it does feel like it's one of these things that is kind of been slowly growing, but it's actually getting I mean, I know these things take longer to build than anyone wants, but it feels like it's got some critical mass.
The hardware on the floor is great. Like seeing all of the like racks from Facebook and then comparing those with like racks from other places. Like,
and there's a lot of nutty ideas out there. There was the rack that was being dunked in water. Like what was up with
mineral oil.
Mineral oil, right? Exactly.
That one was
Fully
insane.
submerged.
Fully submerged.
And then the demo was you ask for your cell phone and drop your cell phone in there, and you're like, whoa, okay.
Okay.
It's
no,
like
thank you.
some sort of weird oil though, because there's like a residue. Like I just put my finger in it.
Yeah.
And then I think the thing that Jess liked the most about OCP Summit is no Kubernetes talks.
It was great. It was refreshing. It was it's like, and then like actually having like a physical thing, like you were saying that you can like touch and feel. Like I felt badly because I made like one of the people at the Facebook booth like pull out this like sled like 14 times so that I could see it. And he was like, this thing is like fairly heavy.
Right, exactly. I'm kind of sweating. It's like, could you just do it maybe 2 or 3 more times?
It was like a bunch of GPUs. It was dope.
That's great. So, but one question about software, because software was not a big part of OCP. I mean, was there any thought in terms of like firmware into OCP, or maybe it was just one step at a time in terms of it's hard to get something like that launched?
Yeah, the initial deployment was designed to be plug and play with.
That's just a low-flying Oakland Police Department helicopter. That's nothing to be worried about. If someone jumps through the backyard, it's fine.
Yeah, and so the initial deployment was designed to be plug and play with existing infrastructure that Facebook had. So changing the software wasn't really part of the equation at that point. And also with a relatively small team, you had to understand, we took a lot on as far as scope goes, and you had to understand what not to do as well.
No, it makes sense. Yep. So there was it was not deliberately trying to keep software out of it. It was just like, this is the part we can go do now. Yeah, right. That makes sense.
Right. Not at all. Yeah. Eventually it did make its way in through different initiatives, through other companies, some through Facebook as well, but not a large part of it. A lot of it started coming into play when networking became bigger and bigger inside OCP.
Yeah, it seems like, and that seems like that was where OCP had its first really big impact across the industry. The in terms of like the networking and that seems where it's had a really outsized impact.
Yeah, that was a lot of fun to experience, where servers for a long time had become commoditized, and networking gear still came at a premium, and a lot of the same thoughts around taking things and just doing them yourself, and realizing that a lot of the networking gear became much simpler to implement and less specialized. Really changed the landscape of how you built networks. A lot of it had to do with the infrastructure, going from switches that were specialty high-speed switches that were large and required a vendor to really put together a fairly complex project, to taking top-of-rack switches and joining them together in a mesh network to be able to replace some of the larger switches there. Really brought together the networking project in a way which allowed it to do a lot of the same things that commoditized hardware.
Right. And basically bringing that revolution. And with the silicon, I mean, you obviously you need that top of rack silicon, but you don't need that expensive surround around.
Correct. Yep. Exactly.
That's great. So, and then, so where to then beyond? I mean, you had your own company. You did the startup journey.
I did. So after 4 years, we had gone from a world where Facebook had purchased servers from the traditional OEMs to going to 100% custom servers. So it was a 4-year evolution there, starting off with compute, then storage, and then flash. Eventually, everything was brought under one roof, and the organization had grown significantly. It was no longer a team of 10 people. There was probably around 200 people if you took into account the engineering and the supply chain, everything that required Facebook to continue to deploy their infrastructure, the physical infrastructure at least. And so things had slowed down a little bit. Obviously, when you're larger, you have your business model figured out, and you tend to take less risks on these things. And that was a good natural progression. That's really where you want to get to. Because you know that you've sort of won at that point. Yeah, I figured out a good formula, and now we're just repeating that, and we still get to benefit and gain from all these cool innovations. That
must have been very satisfying. Like, I've come a long way from the guy who got chewed out for using the thermal paste incorrectly at the The Google DC.
Yep, exactly. And I think most satisfying was really seeing the impact it had as far as energy usage, as far as costs, as far as the community that was built around it and allowing other people to benefit from the same benefits that Facebook had. I tend to like the feature I like the most is really the energy efficiency that came with it. I think that at a high level is a problem that doesn't get a lot of attention.
It doesn't, and it should.
Right.
I mean, you think about like the greenhouse gas emission from our DCs effectively.
Right.
I mean, these are coal burning, natural gas burning power plants that are providing power to these things.
Right. And I think the last statistic I heard is 2% of all energy produced goes to feed data centers.
Wow.
There's some estimates that say it'll get up to 10%. That's a big deal.
It is a big deal.
That's huge.
And it's not a good thing for society or our world in general. And people don't focus on that. Even within OCP, really, it enabled a whole new supply chain, whole new set of vendors. But really what I like to think about is all the emissions that it offset. And so how do you continue that?
Yeah.
How do you get OCP into more hands, more people? It doesn't even need to be OCP, just the same design principles.
Energy efficiency designs.
Exactly.
Yeah, and it does feel like
Exactly.
there's a lot still to be done there in terms of getting, because some of these designs, I mean, it's not controversial that having fewer places for power conversion, for example, is so much more efficient.
Right.
And yet it's still not yet as mainstream as it should be.
Yep. And I think, focusing on that part of it is really, it doesn't, you can try and push that along through the OCP Foundation. I don't think you'll find very many people who will disagree that it's a good thing in general. So enabling traditional vendors or ODMs to build those designs is really a problem that I'm interested in. How do you get that into the hands of more people?
Interesting.
It's too important not to pay attention to. There's too much on the line.
There is too much on the line. Yeah, it's a big, and we don't talk about it enough. I mean, I've always wondered, we as software engineers, I mean, you can have a software bug that effectively results in a lot more power being consumed and a lot more greenhouse gas emission, albeit very indirectly. And we don't really think of it that way right now.
Right.
But we should.
Yeah. Every line of code uses some amount of energy, right? You can count the number of joules that it's using to execute your for loop or whatever part of code you're writing. Yeah.
And I feel with cryptocurrency that got a bit more attention, where people began to realize, like, wow, this is really stupid that we are spending this much energy trying to solve math problems.
Yeah, I hope that's how people view it. I'm not sure yet.
You're right.
It is a very inefficient way of solving a problem that could be done more efficiently, and it's fairly sad to see these big crypto farms popping up, consuming massive amounts of energy. Without much thought to that part of it.
Without much thought. And let's hope let's hope that the consequences for that will be natural and self-enforcing. So was that part of what drove you to Kuhn? I mean, to kind of solving that problem more broadly?
Yes. We were talking about my company then. No, that wasn't it. So naturally going back to where we were at Facebook, things had slowed down. We were making good progress. I always had, growing up in the Valley, this bug that I needed to do a startup. It was something that I was just curious about, something that I wanted to experience. And I decided after my
we empathize with this issue, by the way. If it's not obvious.
I can tell. My younger daughter was born, and I figured I had a new baby at home. What a better time to go ahead and start a startup at that point.
Perfect.
Wow. That's
Right there
intense.
with you.
Yep. And I had a very supportive family. And so I left my job at Facebook and I became more or less an entrepreneur in residence at a VC firm. And I spent about a year thinking about what it was I wanted to do. A lot of what I thought about was how do we get efficient designs and efficient management of servers downstream? Larger companies had great engineering teams, lots of resources that could build management systems. A big part of running efficient infrastructure is utilization. One metric we looked around was mean time to repair. How do you get a server back online after it's failed as quickly as possible so it's not sitting there idle consuming resources? You needed good management tools. Management tools that existed were designed for enterprise. we're talking scales of maybe several hundred servers. Nothing was really designed to allow the management of thousands of servers. We'd built systems both at Google and at Facebook to manage thousands, hundreds of thousands, a million servers at a time. Is that a product that we can actually sell, right? Is that something we could sell, allow people to, as these more and more companies are beginning to scale out, can you sell a product like that that'll help them manage their fleet so they don't need to reinvent the wheel around that?
And manage a hardware fleet. So you're going to be writing software that is going to be talking to a lot of firmware.
Yep.
A lot of BMCs, a lot of biases out there.
Yeah.
And interesting. And presumably discovering how the rest of the world was living in terms of the, I don't know, Jess, you coined the term, I'm sure you coined it, but you talk about the infrastructure privilege that folks at Google and Facebook had.
Yep.
And how do you realize just how little things had progressed since you built your own server back in the day?
That's really when I started realizing that. When I started digging and seeing who is deploying OCP, is there anything meaningful out there as far as deployment goes? What are people still buying today? And it really hadn't changed.
It had not changed.
It looked very similar to the world 5 years prior.
5?
Yeah.
It was similar to
15.
Fry's, right? I assume you assembled that box from Fry's. It looks pretty,
Yeah. Traditional 19-inch one-use servers. And there's lots of reasons why that's not a good design. But it's what people are used to. And it does work, not efficiently, but it does work. And so that was eye-opening. Wasn't part of the problem we were trying to solve.
Right, exactly. Yeah.
Right. And so raised some venture funds, built a small team around it, build a product that, again, had lots of ways it could go wrong, but surprisingly enough, worked really well. And was able to collect billions of data points from server fleets, large server fleets.
Again, you must have discovered some really strange hardware behavior as part of doing this.
For sure. I think the first behavior we discovered was that people weren't necessarily paying attention. And there was so little known about their fleets. The most interesting one was just utilization and just how poor it was.
Yep.
It's something we tracked at scale at larger companies fairly closely, but smaller companies just didn't have time to pay attention to that.
Interesting.
And you would think they would if they're buying. How do they know how many servers to buy? Where is the capacity planning? If your utilizations are that low, are within 2%, 3%. One engagement we had, we actually discovered CPU utilization hovered around 3%. Drives were only around 10% full for spinning drives. Flash was just slightly higher than that. I mean, if you think about the millions of dollars you spend on infrastructure and you're only using it 10% of the time or 10% of its capacity, that's a lot of money you're leaving on the table.
Right. And you can see why a lot of those folks honestly went to utility computing, went to the cloud, where it probably does make sense for a bunch of those folks to.
Yes, although in traditional cloud deployments, you can make those same mistakes there too.
Right.
You reserve an instance, you check out an instance, and you can still just underutilize it as well. Fortunately, in that scenario, the cloud provider may realize and add more tenants onto that particular box. So at least someone is utilizing it. Yes, but you've paid for the full utilization, which you may not be getting. Yep.
When you do wonder, if we could just be omniscient for a moment, how much DRAM is actually being used? Because if I provision a 4 gig instance in AWS,
right,
I'm not going to get that DRAM is not going to be that oversubscribed. I'm basically going to have 4 gig of DRAM, more or less, right? And how much of that DRAM is actually being used, and how much inefficiency is there, and underutilization is there, right? How many capacitors are we lighting up that we actually do not need to be lighting up?
Yeah, I think that's a very true statement where most of it is not being utilized. And with certain things like DRAM, the problem is that there's no power variability. So if you're using it or not, it's consuming the same amount of power.
It's got to be refreshed at the same frequency, right?
At least CPUs can adjust, but things like DRAM cannot.
So that must have been interesting to discover that the rest of the world was not as deliberate about their infrastructure.
Yeah, I guess I wasn't too surprised, but we did see a couple interesting trends. Utilization was low. There was a constant battle at some of these vendors, like to call them second tier companies. So they're not quite hyperscalers. They're a step below. They're running maybe 5,000 to 100,000 servers. Just the resources they had to run efficient fleets were very small relative to the hyperscalers. There was no good solutions for them on the market to help them run that efficiently, and a lot was lacking there. There was very little awareness at the leadership level at these companies that was actually a problem. A lot of them were just happy running the way they were, and so education and awareness was a big part of that. The challenge there is then once you show them that there's an inefficiency, how do you get them to change? And those solutions were lacking as well. So we were more of a visibility solution. There were actions around, hey, here's how you can repair this server faster. Here's the error we saw. Therefore, this component must be swapped. But to actually get them to put in operational procedures to do those things were a challenge too.
Well, also, if I'm managing physical infrastructure, I'm a little bit afraid of your software. I don't know that I want your software to
all
show
the dark corners,
and to show that like just how poor my utilization is. Yeah. And I mean, there's a kind of a human fear of this almost.
Yeah. CYA.
Yeah, absolutely.
Need to keep myself employed, and so we didn't run into that very often. Most of them were very open to understanding what their infrastructure was doing and then use that in order to make a case that they needed more resources.
Right.
Which was good. There was a trend that we were battling, which was the cloud. And so a lot of people, like you mentioned, were just fed up and said, look, it's easier to do these types of things in the cloud because we get all these amazing tools that help us manage. And the hairy problems that we don't want to deal with, our cloud vendor takes care of that, hardware and things like that. And for many businesses, it is absolutely the right decision to make to go into the cloud. Not for every business, though. There are those with requirements where they can be a lot more efficient on their own too. And so it's all case by case. And we would help customers understand that and at least provide more data so they could make a decision that was right for them.
And did you find that it was hard? I mean, so one of the challenges that you have is you're writing this layer of software that's sitting pretty low in the stack. Because you're talking directly, I assume, you're talking to firmware to get a lot of information out of the box.
Yep.
And I mean, you must discover like things that are numbers that are wrong, things that are being...
Yeah, there was a lot of, when it comes down to low-level firmware, there's a lot of areas where vendors don't do a good job writing the firmware. Some examples that made things a challenge, really basic things. You would get a box or a customer would have a fleet of systems from HP, and you would query a field that was supposed to tell you what vendor manufactured the box. And sometimes you would get Hewlett-Packard, sometimes you get HP, sometimes you get HPE, sometimes you would get different spellings of different things, and it made it hard to actually understand what you were dealing with. And so we solved a lot of that through software, where we would look at the different variations and then understand that they were the same thing, and then normalize those variables. And the customers always like that.
Right.
Lots of DRAM vendors would forget to program registers that identified their part number. And so you had to stick a DRAM and you'd look at the model and it would be zeros.
Right.
Or
it's OEM.
Exactly. Or something else. And so creating, and consumers wouldn't realize this. No one looks at those details until you actually want to do something with that and say, hey, I'd like to find out where all of my micron memory is. But surprise, surprise, it's not all labeled.
Right.
And if you have an error, that's very costly, right? Because you don't know which boxes to swap if you needed to, for example. And so those were some of the things that we came across, and it just requires, it's hard to solve those in software. It requires humans to do the right thing in writing specifications and asking vendors to follow those specifications.
Yeah, and I think we in software end up we're the ones that end up having to paper over it. I don't know, make the different spellings of Hewlett-Packard look the same, right? I mean, you have to end up having to bury all the bodies there.
Yep. And depending on what version of firmware you had, errors would be reported differently. For example, you could count errors, single bit errors in DRAM, which were covered by ECC, but then you wanted to understand which ones had more errors. And the counting of the errors was different. Some of them would report a raw number. Some of them would count one error for every 10 physical errors. So you didn't know if you had one error or 10. And just the standards that were fairly lax across all of the firmware vendors. And so it was always a challenge to really understand what was going on with the hardware. Oftentimes you'd have to often go to the vendor and ask what they were doing.
And this stuff is super important because those error accounts, I mean, those can be your wisps of smoke that can indicate something serious.
Exactly.
I mean, those correctables may actually be the thing that you need to be able to react to,
right,
to be able to resolve a serious problem.
Right. You'd like to know what the trends are. If it stays, and we found really interesting trends, right? If errors stayed somewhat constant at a constant rate, well, the DRAM would usually chug along. As soon as there was an uptick in those errors, you knew it was going to fail within a certain confidence level.
Right.
But you know, if you can't even count what they are, it's going to be a hard time.
And if you know that something's going to fail, you can actually react in advance.
Right.
You can actually take action.
Right. That was a lot of our selling points. Look, we will predict a failure. And you can do that fairly well today on hard drives, on DRAM and things like that. There's a number of papers that are written about it. There's one company called Backblaze.
Yeah, right. Their stats are great, aren't they?
They share a lot of those.
They share a lot of them. I know. It's so great.
Yep. And that was a good way for us to train some of our algorithms initially.
You use the Backblaze data.
Oh, yeah.
Yeah, interesting.
Yeah. We worked with them on that. We found a number of things.
Jess, have you looked at the Backblaze data?
No, I didn't realize that it was open, but I know of Backblaze.
Well,
cool.
so Backblaze, yeah, and they basically looked at their failure rates across the fleet, and they basically name and shame ultimately by
That's dope.
Yeah,
by spindle and firmware rev.
Right.
And speaking as someone for whom a particular firmware rev from a particular drive vendor had a serious impact crater in my life, like this is great information. You can go look at.
Yeah, they would nervously anticipate the release of the next report.
Oh, absolutely. Oh, I think you are terrified if you.
Backblaze reports coming out.
Well, especially if they don't buy very many. So if they buy 100 of them, and 2 of them fail,
right,
their numbers are going to be off the chart. So it's like you want to sell Backblaze nothing, or you want to sell them as much as you physically can, because then the numbers are, and because they are not many folks do that. I mean, they don't.
Yeah, I definitely tip my hat to them for starting that trend.
Yes.
The idea with Coolan and every customer that sent us data, part of our legal agreement was that we could use that data anonymously.
Really? Oh,
interesting. And the idea was to do what Backblaze was doing, but do it across more components at a larger scale too. Now you have it coming from different environments, different systems. How does OneDrive interact with one particular motherboard?
Right.
How does one firmware fan control algorithm, which cools differently in an HP system than a Dell system, result in failure rates across different components? And so to have a much larger pool of data and be able to share that anonymously, because there's only so much data you can crunch yourself, but with the community was part of the idea too.
That's a great idea.
It's still something we didn't quite get to that, unfortunately.
It's a hard one because you would ideally, all the vendors should want to collaborate to get these problems solved.
Yes.
But that's not always the
should
ideal world.
What we found was that vendors wanted access to the data. Some of them were even willing to pay for it because it's hard for them to get field data. That was step one that we discovered. We didn't quite get to to publicly posting any of the data, and that basically had to do with the business of the startup.
Right.
It would have taken a few more years to get there, and continuing the business became a challenge for us.
It's tough. It's a tough software to write, and then it's tough to sell. But so unfortunately, Salesforce obviously saw a lot of value in it. Yeah.
So at some point we came to you get funding, and this is a good point for you guys, and that's when the clock starts ticking, and you have a certain window for where you need to show enough value so that other investors will come and agree to give you more money. You can get enough revenue from customers to keep yourselves afloat, or you can shut down the company, or you can sell the company. And we got far along enough where we had some value, we had revenue coming in. We had a hard time raising more money from ventures, primarily because a lot of venture operators had this thesis that things were moving to the cloud and owned infrastructure was going away.
We are familiar with this thesis.
Yeah.
Heard that.
We are very contrarian.
We've heard this a couple of times.
Yep. Yeah. And so I had a hard time convincing them that infrastructure was going to continue to run outside of the hyperscalers. Some of them weren't even interested in hearing some of the reasoning behind it. They said, sorry, we operate in this way. We're not going to entertain a conversation.
Right. And when you kind of phrase it, it's like, so do you believe that Jeff Bezos is going to own and operate every computer on the planet? Like, well, no, of course not.
Right.
We just think that everything is moving to the public cloud. Right. And on that public cloud is going to be AWS. I'm like, okay.
Exactly. And like I said before, there's many reasons why running your own infrastructure makes sense. Before you didn't have a choice. Now you have a choice, and you have to make the evaluation if it makes sense. And I don't know if you want to go into the reasons of when it does, but it does. In some cases. And I don't think many companies are equipped to make that evaluation on their own. It's a fairly thorough evaluation. I've done it several times. But no, there will be infrastructure outside of the cloud. There's no doubt about that.
Totally. I mean, we definitely believe that.
And even as that expertise is being lost, I mean, I remember in 2011 at Surge asking show of hands how many people had stood up their own physical infrastructure, and only a quarter of the hands went up in 2011.
Wow. Yep.
And that number's not going. I mean, so I think that that's part of the challenge is that those people that are still deploying physical servers feel like the world has left them behind.
Right. It doesn't need to be that way. Look, it's not rocket science. With a team of 10 people, we did a completely custom rack and server and power supply design for Facebook. You're not sending an order to the moon or anything like that. You're building server infrastructure, and with talented software engineers, you can manage it well.
Okay,
it doesn't require
thank you
huge
very
armies.
much for differentiating this from the Apollo program. I get so sick of being like, wow, this is a moonshot. It's like
actually,
easy. This is not a moonshot. The Apollo program was actually
A little more tricky,
little more ambitious.
Yep.
And, because the flip side of all of this is that the infrastructure is more accessible than ever before. I mean, if somebody, OCP, you look at how much is available via OCP.
Yep.
Open source software, open source firmware.
Yep.
And if people want to get interested in this stuff, it's way more accessible than it ever has been.
Yep. You have to have right sponsorship, right leadership directions, a small willingness to invest in smart people to do this, but it's totally possible.
And a lot of people have worked out some of the really hard problems. I mean, you were the Busbar in the OCP design. You had a great anecdote about the safety of that.
Right. A lot of it, I would call it FUD, right? Fear, uncertainty, and doubt. And that came up many times throughout the development of the project. The Busbar you mentioned runs 48 volts, and it was used to back up the servers when the main primary power source failed. And so you'd get these large copper busways with, this was in the battery cabinet with, thousands of amps running through them at 48 volts. And it's counterintuitive, but 48 volts isn't enough potential to draw enough current through the human body to cause any sort of you don't even feel it.
Right. So it's like, on the one hand, like you can think of 48 volts. On the other hand, thousands of amps is enough to absolutely kill you.
Right.
So it's like, you've got to you touch that first.
Right. So we'd sit there and almost play chicken, right?
Right.
Who wants to touch it? We know it's not going to do anything.
Okay, I am the software guy. I'm at the back of the line. I will let everyone else touch it first. So who touched it first?
Right. So our power engineer, Pierre Luigi, said, come on, guys. We
Get
know.
out of my way.
And he stepped aside, touched the bus bar as we were discharging the batteries into it, and nothing happened, right? So I said, oh, cool.
All right, me next.
And touched it, right? And then I think we're the only two who touched it. But the fear of, hey, something could happen, I don't quite understand it. I don't see it. Definitely was a factor there. And it kept going for many things within the project too. One other thing we did, quick anecdote, was we took off the BMC from the server. How do you run a server without a management controller? For those who don't know, it's a small little processor that sits on the server, and it pulls a couple of bits of information and sends them back over a management network. So you could still control the server even though your operating system had crashed or your kernel had crashed. And we looked at it and we said, look, it's primarily used to reboot boxes, and that is all. No one was using it for much more other than that. If you want to collect metrics from the box, it's always better to go through the operating system.
Yeah, exactly.
You get
right.
way more information that way. You're limited by whatever whoever wrote the BMC firmware or the management controller firmware did, and they never thought of every bit of information you wanted to pull from the box. So you just went from the operating system. We said, great. We're just going to get rid of this BMC because we're not using it except for rebooting the box. And of course, up in arms.
Right. Heresy. Heresy.
How could you run? What if someone, messes something up? and you need to get to the box and the kernel's crashed. And I said, look, then you got other problems. But we'll be able to reboot the box. What we did is we took this thing called the magic packet, which was a special Ethernet packet you could send to a host, and it would cause the host, at the time, it was designed to cause it to wake. So you'd put a host in a sleep state, and you sent it the magic packet, and it would wake on LAN, is what we called it.
Wake on LAN.
Wow.
It depends.
It doesn't depend. It's wake on LAN. It doesn't depend on anything. It's not wake on LAN.
It depends.
And so,
I was actually setting LAN is the magic packet for Jess. That's what actually wakes Jess up. Exactly.
nice. So instead of tying that to the wake on LAN signal from the Ethernet controller, we tied it to the reboot signal. Obviously, we did some things to make it secure because you don't want to broadcast this packet across your network.
But what a story that would be.
And have
what a story that would be.
We didn't want the whole cluster to reboot. But we implemented that in the first version of OCP, and we cut out $40 from the bill of materials from a box, which was fairly significant.
Right, to eliminate the BMC.
And we deployed, and it worked. And it was working just fine until...
The BMC industrial complex got wind of this.
No, not quite. Until someone fat-fingered a command and re-IP'd several hundred memcache servers in the cluster. So think of a cluster that and the memcache server sits between the database and the web server, and it serves out 99% of the queries because everything's hot and cached, and your database tier can be much smaller at that point.
Right.
And so these memcache servers went offline, and you take
no problem. We'll just go to the database.
Doesn't work. You take the cluster down, and to bring it back up takes about 24 hours because you have to warm up the memcache servers again. And that happened, and they said, look, luckily this had happened in an older cluster that didn't have OCP servers in. And what did they do to fix it? They logged in through the BMC and re-IP'd all the machines to their proper addresses that way because you could get console access through the BMC and re-IP them. And said, look, thank God we had this BMC. We didn't require us to wait 24 hours to restart this cluster. And they came to me and said, look, Amir, this is a problem. See what happened. This is why you need a BMC on the box. And I said, is that really the problem? Or is the problem that you allowed someone to re-IP a bunch of servers and didn't have any safety protections in there?
Right.
Right.
They don't want to hear that answer.
That wasn't the problem.
Yeah, exactly.
The problem was the BMC.
Yeah, exactly. The problem is the BMC.
So in the next generation of servers, the BMC came back.
The BMC returned.
Nice.
Yep.
Interesting. So in terms of going forward, I mean, we feel that the lost art of deploying hardware is going to come back. What's your take on it?
I don't think it ever disappeared. I think people's willingness to want to do that has been diminishing, but the talent is still there. The ability to do that is even more so present today than it used to be. With, like you mentioned, lots of open source tools that can help you deploy.
I mean, you can make your own microprocessor, right? You think like in terms of like people taking. It's amazing how much you can go do.
Yeah.
And people being able to do FPGAs on their own. A logic analyzer is like $100 now or whatever.
Yep. You have to have the right people and the willingness to do it, but it's definitely possible. And for the right cases, you can save a ton of money and be more efficient that way too. So, with that, it's going to be a constant pool. And if you think about who's making the decisions, oftentimes, it's not necessarily an infrastructure-based decision always. It's around agility and your ability to put your product out on the market faster. If you don't have a team that's performing well, and as far as your infrastructure goes, and you want to release a product and they become a bottleneck, well, it doesn't really matter. You're just going to go to the cloud because you have a business to run and your business is selling a product. And if you don't have a factory internally that can build your product for you, then you go to the cloud, right? If there's an easy way to do that, I think then there's a much better case for building your own infrastructure.
God, someone should start a company.
I agree.
I like the way you're thinking, Amir.
Good. That
is great. Well, Amir, this has been great. This has been a lot of fun to hear about your career and a lot of interesting, exciting stuff at the hardware software interface. If people want to learn more about you and about what's your social media of choice?
You can find me at Facebook.com/Amir. On Twitter, I'm DigiAmir, D-I-G-I Amir. And more than happy to connect.
Awesome. Well, I thank you very much for your time. Thank you for joining us in the garage. This has been a lot of fun.
Yeah, thank you.
Thank you.
My pleasure. Thanks for having me.
You've been listening to On the Metal, Tales from the Hardware Software Interface. For show notes, to learn more about our guests, or to sign up for our mailing list, visit us at onthemetal.fm. On the Metal is a production of Oxide Computer Company and is recorded in the Oxide Garage in Oakland, California. To learn more about Oxide, visit us at oxide.computer. On the Metal is hosted by me, Bryan Cantrill, along with Jess Frazelle, and we are frequently joined by our boss, Steve Tuck. Our original and awesome theme music is by JJ Wiesler at Pollen Music Group. You can learn more about JJ and Pollen at pollenmusicgroup.com. We are edited and produced by Chris Hill and his crew at HumblePod. From Jess, from Steve, from me, and from all of us at Oxide Computer Company, thanks for listening to On the Metal.